Sports, and we're going to be looking at a video about approaching the Pythagorean theorem from the viewpoint of quadratics. A lot of people often wonder why the Pythagorean theorem, an 8th grade standard, is stuck into the third topic of the quadratics unit of Algebra 1. One of the best connections is that because the Pythagorean theorem can actually be derived using quadratics and solving quadratics. So in this video, we're going to be talking about solving or deriving the Pythagorean theorem algebraically using those quadratic features. So let's think about the Pythagorean theorem algebraically. We're going to start with an image of two squares, one within the other. We have to start asking students some things that they notice. One of the things that they may pick up on right away is that C is the hypotenuse for each of these smaller triangles. They may also pick up that all four of the smaller triangles have a length and a height of A and B. So we now want them to start using that information in a meaningful way. One of the things we want to ask them about is the area of the larger square. And we want them to pick up on the fact that the larger square is the square of the quantity a plus b. And that's because the length of the larger square is a plus b. The entire length is the sum of those two variables. The area of the smaller square is just c squared. We also want them to think about the area of each triangle and the area of the four triangles. Since the formula for the area of a triangle is 1/2 a times b, and we have four of them, we're going to have 4 times 1/2 times a times b. We should also know that the area of those shapes can be done by subtracting the smaller square from the area of the larger square. So if we have the square of a plus b, and we subtract out the area of the smaller square, c squared, we get the area of those four triangles. Because we know that both of these expressions represent the area of the four triangles, we can set them equal to each other and solve. So we're going to have 4 of those 1/2 a times b equal to the square of the quantity a plus b minus c squared. 4 times 1/2 is just 2, so the left side is 2ab. We can now square that a plus b term. 2ab equals a squared plus 2ab plus b squared, and still minus c squared. At this point, we want to ask students if there's something that they notice right away. They should be able to pick up that there's a 2ab in both sides of the equation, and therefore we can eliminate it, which means that 0 equals a squared plus b squared minus c squared. Now the Pythagorean theorem isn't stated that way, so let's go ahead and add the c squared to both sides, and we have our Pythagorean theorem. C squared is equal to the sum of the squares of the other two sides. Let's go ahead and use this in a typical Pythagorean theorem task, particularly in the Algebra 1 context. Here we have a right triangle presented on the coordinate plane. One of the things that we would ask students to do is to determine the length of C. Now, on a coordinate plane, it's important for students to recognize that if the scale factor for the x and y axis is just 1, they know the length of A and B just by counting. And actually, that's a better place to start than diving into the distance formula. So we're going to start with the fact that we know that c squared is equal to a squared plus b squared. The length of A is just 3 units. The length of B is 4 units. So c squared is equal to 3 squared plus 4 squared. C squared is equal to 9 plus 16. C squared is 25. And C is 25. A lot of teachers want to use this opportunity to teach the distance formula, and it's a great opportunity to do so. We're combining our algebraic reasoning with the coordinate geometry. It's a perfect place to do that. So what we want students to recognize is that for any points, we can figure out the distance between those 2 points by subtracting. If we look at the x-coordinates and we look at length a, 5 minus 2 is 3. If we look at the distance for b, 4, we can actually get that 4 by doing the distance or the difference of the y-coordinates, 2 minus minus 2. And because we can just take the difference of those 2 coordinates to figure out the x and y lengths, our distance is just the square root of the square of the quantity x2 minus x1 plus the square of the quantity y2 minus y1. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.